Hi everybody, welcome to our Hess's Law Lab. What we are going to attempt to do is we are going to attempt to figure out what the heat of reaction is for this reaction by being given that reaction and then calculating what these two guys here are. So what we're first going to do is we're going to do step one, which is to take 100 milliliters of 1 molar hydrochloric acid and add in about a gram of magnesium oxide to it. So I have all of that material set up right here. So what I've got here is I have got 100 milliliters of hydrochloric acid, 1 molar hydrochloric acid. And again, you'll just have to trust me that that's the case. So that's 100 milliliters of 1 molar hydrochloric acid. And then I have got 1 gram of magnesium oxide that is there. So here is the magnesium oxide that I've been using. There it is. Now, to do this, we're going to have to make a couple of assumptions, the first of which is that the specific heat of the hydrochloric acid is going to be the same as that as water. It's not, but it should be pretty close, but it is a source of error to think about. So I'm going to take that hydrochloric acid and I'm going to put it into my very fancy calorimeter that is here, and I am then going to put in a thermometer and stir that around and make sure that I get an accurate temperature here for my hydrochloric acid so that I know where it's going to start. And it looks to me like it's starting, again, you can't really tell from where you are, but it looks to me that it's about 23. So I'm starting at 23 degrees Celsius here with this. Now, what's going to happen is that I'm going to take the magnesium oxide that is here, and I'm going to put that into that container, and we're going to get a chemical reaction out of it. And as the chemical reaction goes, it's actually going to be an exothermic reaction, which means that the temperature of this guy is going to increase. Because again, what we are doing is we are counting this as our system. It's losing energy, and we are figuring out how much energy that my system is losing by measuring the surroundings, which is going to be the water that is in the hydrochloric acid solution. So we started here at 23 degrees Celsius, and I have 1 gram of magnesium oxide put into 100 milliliters of the hydrochloric acid, which we are kind of assuming is water, but it's not quite exactly. So here I go. I'm going to go ahead and put in my magnesium oxide, and all that magnesium oxide goes in. Sorry, again, it's real tough to do these things by yourself. So that goes in, and we give that a stir, stir, stir. And as this guy here gets stirred up, then you are going to see an exothermic reaction occur, and the energy is going to be given off by the chemical reaction, absorbed by the surroundings, which we are going to assume is our water. That is the aqueous solution of our hydrochloric acid. And again, we're making a bunch of assumptions here that are not quite true, but are pretty close. And after we have given that a shake, 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 then we can check out the final temperature here. I'm not sure that it's completely done. I'm not convinced that it's finished yet, so I'm going to give that just a minute more. So this is the exciting part where we fast forward. So I'm going to make sure all of that reaction is good and reacted. I know it's done when the temperature stops going up. So at this point, our temperature is topped out at about 31 degrees Celsius. So again, our temperature here is topped out at about 31 degrees Celsius. So I started at 23, it went to 31, which is an increase of 8 degrees Celsius for reacting 1 gram of the magnesium oxide in with the hydrochloric acid. Armed with that knowledge, we should actually be able to figure out what the delta H of the reaction is. All right, for part 2 of the experiment, what we're going to do is we're going to do the exact same thing, except that we are going to do our second reaction, which is the magnesium plus the hydrochloric acid. That's going to turn into the magnesium chloride and hydrogen gas. Now, in order to do that, according to the information here, we're going to start with 50 milliliters of the 1 molar hydrochloric acid and put in 0.2 grams of magnesium. I have both of those things all set and ready to go here. That is 0.2 grams of magnesium ribbon, and that is 50 milliliters of our hydrochloric acid. So I'm going to go ahead and put in our hydrochloric acid into the high-tech calorimeter here, and again I am going to take its temperature here so that I know where it is starting. Once again, we're going to cheat. We're going to assume that the hydrochloric acid is mostly water, which it mostly is, but the standard numbers for water are technically not the case here, but we're going to assume that they are, and it's going to get us close at any rate to the specifics. All right, so starting here, it looks like I am starting at about 23 degrees Celsius. That's where I am starting here. And now what I'm going to do is I'm going to take my piece of magnesium and I'm going to put it in there, and it's going to react like crazy. Once again, it's going to be an exothermic reaction. The reaction is going to give off energy, and that energy is going to be captured by the water, which is going to be our surroundings, and our magnesium here and the hydrochloric acid is our system. And so it is going to be a negative delta H because it's an exothermic process, because the water is going to get hot here. So I got my lid, I've got my magnesium here. I'm going to dump in my magnesium and put in my thermometer, and I am going to give that a shake, 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 and give that some time to react here. So I've got 50 grams of water essentially that is absorbing whatever amount of energy that is going to be coming from the magnesium and the hydrochloric acid reaction. So as soon as that is done reacting, the temperature will stop going up. I'll take the lid off, and then we can figure out what the final temperature is. I don't know if it's coming through, but I can hear the reaction still occurring here. So I can hear the bubbling occurring here. And that bubbling is because of the production of the hydrogen gas that is over here. All right? All right, the reaction is now done. There is no more magnesium that is in there. It's been reacted all away, and it looks like, wow, it looks like our temperature went up to 40 degrees Celsius here. So our temperature topped out at 40 degrees Celsius. So knowing all of that, we should now be able to figure out what the delta H of this reaction is. Hi everybody, here's the calculations part of this lab. So what we're going to try to do is we are going to try to combine our knowledge of enthalpy so that we can figure out what these delta H's are, and then use all of these equations to get this guy here by the idea of Hess's law. So the first thing that we need to do for each of these guys is do the calculations. We need to figure out this guy here and what his delta H is. Now this is the experiment that we did. We took the magnesium oxide white powder and put it in with hydrochloric acid, and then measured the energy that was coming out of there. We're going to have to make some assumptions. They're not going to be quite perfect. There's going to be some error that is involved, and we're going to hope that that error is very small in comparison to the overall ease that it gains us in being able to avoid those errors. So what are those errors and how is the calculations going to work? Well, let's take a look at everything. First of all, let's take a look at our data. So in part 1, we did 100 milliliters of 1 molar hydrochloric acid, 1 gram of the magnesium oxide, and it went from 23 to 31. So what are the assumptions and what is the problem here? Well, first of all, we've got 100 milliliters of 1 molar hydrochloric acid. We should have the specific heat capacity of an aqueous hydrochloric acid solution and so forth and so on, but we don't. But we can take advantage of the fact that a 1 molar hydrochloric acid solution is really mostly water. So if it's really mostly water, then what we're going to do is assume a couple of things. We're going to assume that what we have is 100 grams of our water solution.
because we know that the specific heat of water is 4.18 joules per gram degree Celsius, right? And again, we know that it's 100 grams because the density of water is 1, so the 100 milliliters should give us 100 grams. That's not quite true, but it's going to be approximately true. It's going to be really close to true. So what we've really got here then is we have got the hydrochloric acid and the magnesium oxide that are in this water solution here that are reacting, and this reaction is exothermic and it's going to give off heat to the water. And we are not going to measure this reaction directly. What we are going to do is we are going to be measuring the effect that this has on the water solution with our thermometer in there. And we're going to assume that anything that this red reaction gave off, the water absorbed. So that's assumption number 1. We're going to assume that what we have is 100 grams of the water, right? However, having said that, what we've really got is 101 grams. Well, where'd the extra 1 come from? Don't forget that we added in 1 gram of magnesium oxide. So in reality, what we've got here is we've got about 101 grams of substances that are actually changing temperature in this. And on the AP test, they're going to want you to include that extra 1 gram from the solute that is going in there. So again, we've got a couple of little assumptions there, but that's going to get us pretty close to what is going on. So that's our data there for part 1. So let's run through the calculations then for part 1. They are down here in this guy. So it says calculate the heat that the reaction we'll really calculate the heat that the water absorbed. So what I'd like to be able to do is I'd like to be able to calculate the heat, the Q, the heat of the amount that was absorbed by the calorimeter process itself. So that is going to be equal to MC delta T, or if you'd prefer, TF minus TI, right? Okay, and we want the Q that the water calorimeter system absorbed. Really, it's the hydrochloric acid and the magnesium oxide, but again, we're assuming that it's mostly water. So, like I just said, our mass we're going to put as 101 grams because we've got the 100 grams of the hydrochloric acid. It's probably not exactly 100 grams, but it's pretty close. And the 1 gram of the magnesium oxide. We're also going to assume that it's 4.18 joules per gram degree Celsius because, again, it's mostly water. And then the temperature change of it was, that's part 2, is the 23 to 31. And so our temperature change is going to be 31 minus 23 degrees Celsius there. And so if you get out your calculators and do a little mathification here, I got 101 at 4.18 at 8, essentially, 31 minus 23, gets me about 3377 joules. So this is 3377 joules, and that is the heat that the water absorbed. So the water absorbed 3377 joules. Now, what does that mean? Well, if the water absorbed that much heat, that must mean that this reaction that we put together in there gave off that much heat. Because remember, Q lost equals negative Q gained. Or the Q of the reaction is going to be the opposite of the Q that the hydrochloric acid solution and everything absorbed. So that's pretty darn easy. Then the Q of the reaction is going to be equal to negative 3377 joules, right? All right, now part 3 says calculate the moles of the magnesium oxide used in the reaction by using the mass. We're assuming that the magnesium oxide is the limiting reagent, and I could prove it, but I don't feel like it. So if you want to go through and prove that the magnesium oxide is the limiting reagent, you can. Otherwise, just trust me that the magnesium oxide is the limiting reagent. So because it's the limiting reagent, then we're going to have 1.0 grams of the magnesium oxide at 1 mole per 40.3 grams. Again, you should be able to very easily figure out that magnesium is 24.3, oxygen is 16. Add those together and you get 40.3 grams per mole. So 1 gram of the magnesium oxide at 40.3 grams per mole gets me 0.0248 moles. Please note that I have taken this to at least 3 significant figures. And I didn't just stop at the 3rd decimal place there. I went to 3 significant figures. That is there. So technically speaking, if I had done the same thing up here, I should be at like 3380 for this guy in order to get to 3 significant figures. So again, had we changed that to 3 significant figures, that would be 3380, because I'd like everything done to 3 significant figures. All right, so now all we got to do is calculate the delta H. Well, what is the delta H? Delta H is the Q per the mole. So you want it on a per molar basis. So I'm going to go ahead and plug things in here. The delta H is going to be the Q of the reaction per the moles that actually reacted. So that's going to be our negative 3380 joules. That's the Q of the reaction, divided by the moles, which is that guy there. So we're going to divide that by 0.0248 moles. And when you do the math on that, 3380 divided by 0.0248, you should get in the vicinity of negative 136,290 joules per mole. Or if we round that to kilojoules, then that's going to be negative 136 kilojoules per mole to 3 significant figures. So the delta H for this process here is negative 136 kilojoules per mole. Reaction number 2 is done the exact same way, except that it is done with this equation instead of the other one. So what did we do for that one? Well, in part 2, we had 50 milliliters of 1 molar hydrochloric acid. Again, we're going to assume that that is mostly water, so it's got a density of 1 gram per milliliter, which is going to give us 50 grams, and it's got a specific heat capacity of 4.18. So we're just going to go ahead and assume that we're talking about 50 grams. But don't forget that we're going to be putting in 0.2 grams of magnesium. So in reality, when we're sticking our thermometer in here, we're going to have a total of 50.2 grams of solution, overall solution, that is going to be changing temperature and so forth. Once again, we are going to try to figure out what the delta H of the reaction is, but we are calculating the delta H of the reaction based upon the surroundings. So this is our system, but we are actually measuring the surroundings, which is why when the surroundings get hot, we know it's an exothermic reaction, and therefore the delta H should be negative. So let's walk through the calculations on that the exact same way. So the Q of the water calorimeter solution is going to be 50.2 grams, the 50 grams of the hydrochloric acid and the 0.2 grams of the magnesium, times a 4.18 joules per gram degree Celsius. That is the specific heat capacity of the mostly water. Not quite true, but close enough. And then we need TF minus TI, so we need the temperature change. And the temperature change for this one went from 23 up to 40. So again, that's going to be 40 minus 23 degrees Celsius, which is 17. So we're going to have 17 degrees Celsius at 4.18 at 50.2 is positive 3570 joules for that to occur to 3 significant figures. Once again, that is the surroundings, but what we're really interested in is the system, our reaction, and so the Q of the reaction is going to be the opposite of the Q of the surroundings. So the Q of our reaction is going to be negative 3570 joules. we're going to assume that the magnesium is the limiting reagent. It is. I don't want to prove it to you. Just assume that I am correct here. So I have 0.20 grams of magnesium divided by 1 mole per 24.3 grams. Again, if you're really interested in me proving it to you, I could prove to you that this is the limiting reagent, but that's not really what this question is about. And I get 0.008, but again, that's only one significant figure. It's in the third place, but it's only one significant figure. So consequently, we go 2 more decimal places, and I've got 23 there. Now I have 3 significant figures, not 3 decimal places. So then the delta H is going to be equal to the negative 3570 joules divided by the 0.00823 moles. And so 3570 divided by the 00823 moles is going to get me an overall value of negative 433,779 joules per mole. That's way too many significant figures, and our number is inconveniently large. So consequently, I'm going to change that to negative 434 kilojoules per mole here. So our second equation that was up here is negative 434 kilojoules per mole. All right, so we're 2/3 of the way there. Negative 136 and negative 434. Let's go down to our worksheet here. So negative 136 and negative 434. Now that we've got those, what we're going to do is I'd like us to use these 3 reactions to add up in order to get this reaction, because this is what I actually want. So this is Hess's law. And we're going to reversify or multiply or divide or change the sign or whatever it is that we need to do so that these 3 equations, and only these 3 equations, add up to be this equation down here. So like we said in the lecture, what I like to do is I like to find something that is in my equation here that is only in this equation here and only in one place down here. And so if we look closely at this, we see that the magnesium oxide is down here, and there is no other place that magnesium oxide exists. So that's the thing that I'd like to key on here. So I need 1 mole of magnesium oxide on the right. Well, I've got 1 mole of magnesium oxide, but it is on the left side. So consequently, I'm going to rewrite this equation backwards. And I'm going to write it as MgCl2, and that's aqueous, plus a water, which is in liquid form. And that's going to come over here to form my magnesium oxide, which is a solid, and 2 hydrochloric acids, which are aqueous. And because I have flipped this equation, I take my delta H and I reverse its sign. So instead of being negative 136, that's going to have a delta H here of positive 136. So my first step here is going to be positive 136. All right, fine. So that's done now. Now, what is going on here that is down here and only down there? Well, I'm looking at the magnesium. The magnesium is here. The magnesium does not appear anywhere up here, just magnesium, the solid magnesium, nor does it appear here, and we do need it down here. So what do I need? I need 1 mole of it, and I need it on the left. I've got 1 mole of it, and it's already on the left, so I'm good to go. So I don't have to do anything to this. I just have to copy it. So this is magnesium solid plus 2 hydrochloric acids. Aqueous is going to come over here to form magnesium chloride, aqueous, and hydrogen gas. And that's going to be negative 434 because, again, that did not change. Alrighty, let's see, what can I do now with my third equation? Well, is there anything here in my third equation which appears only down here and nowhere else? Well, it actually turns out that the oxygen does in this particular case. there's half an oxygen on the left-hand side, and I need half an oxygen over here on the left-hand side, and oxygen, O2, does not appear anywhere else in any of these other equations, so great. If that's the case, then I'm just going to take this equation, because I've got everything I need, and I'm going to copy it down. So I have hydrogen gas plus half of an oxygen gas is going to come over here and form a liquid water. And that is negative 286 according to that number. So let's double checkify that everything is going to cancel out and give us what we want. So first of all, I've got my half of an oxygen here. I have got my magnesium that is here. Here's my half of an oxygen that's there. And I need my magnesium oxide. So here's my magnesium oxide, and I have it there. So I have everything I need, which means everything else should cancel out if I have done it properly. I have got an MgCl2 on the left, and I've got an MgCl2 on the right. I've got an H2O that is on the left-hand side over here, and I've got an H2O that is on the right-hand side over here. I have got 2 hydrochloric acid aqueuses over on the right. I've got 2 hydrochloric acid aqueuses over here on the left. And I have got a hydrogen gas on the right, and I have got a hydrogen gas on the left. So the only thing that I am left with from this is my magnesium, my oxygen, and my magnesium oxide. And once you get to that point, all you have to do is add these bad boys up. So I have 136 and a negative 434 and a negative 286. And I got an overall answer then for my equation of negative 584 kilojoules per mole as my delta H of the reaction. Is that good? Is that bad? Is that anywhere in the ballpark? Well, according to this, the correct answer should have been negative 602 kilojoules per mole. So wow, yeah, I did a really good job here. That is some fantastic data. That is not much error. So our last part here says calculate the percent error. So what is percent error? Percent error is the absolute value of did minus shoulda over shoulda. Huh? What did I get? Subtract what I should have gotten, and then divide it by what I should have gotten times 100%. So I did get negative 584. I'm going to subtract from that what I should have gotten, which is negative 602, and then I'm going to divide that by negative 602 and take the absolute value times 100%. So when I'm all said and done, 584 and 602 divided by 602, I got a 3% error, a 2.99% error. So that should have been a 2.99% error. That's pretty darn good. 97% accuracy, even with our assumptions and even with our high-tech styrofoam calorimeters. So this kind of combines a whole bunch of stuff that we learned in class. It's a great lab with fantastic results.